Hey there students, Mr. Hugo here. In our video today, we're going to be looking at one of the questions from homework 2, dealing with our study of kinematics. So this question, depending on the year you're watching this video, is likely going to be toward the end of your homework assignment, and there's a few parts, kind of layers to the problem that we're going to talk through. So I'll read the problem for us and then we'll get started. Here's our problem statement. A record of travel along a straight path is as follows. So we're going to be given a few steps here about a record of travel. So how an object is moving. So our object starts from rest with a constant acceleration of 3.08 meters per second squared for 12.6 seconds. Then we move with a constant velocity of 38.8 meters per second for the next 0.824 minutes. And then a constant negative acceleration of negative 11.8 meters per second squared for 4.09 seconds. The question wants to know what's the total displacement for the complete trip. So there are what appears to be 3 separate parts to our trip here. So what we're trying to do is find the overall displacement, which means, well, we need to find the displacement for each part and then maybe sum those up. So let's start with part 1 here. We're going to treat this as if it's just, again, 3 separate problems, and then we'll look at our solutions at the end. So in each set, we're looking for delta x, the displacement of our object. So I'm going to put a star by delta x, that's what I want. Initial velocity, final velocity, acceleration, and time. Okay, so let's take into account what we know for this first part. In fact, I may call this part A because that's the labeling used in the problem. Again, your numbers will be different than mine, but the process should be relatively similar. So we're starting from rest, so my initial velocity will be 0. We're told we have a constant acceleration of 3.08 meters per second squared, so a little bit below average, and if we're dealing with something like a car, for 12.6 seconds. Okay, so it looks like V1 is the thing we don't know, and we're not really concerned with, so I'm going to cross out V1. Which tells me I should likely use equation number 2. Delta x is equal to initial velocity times time plus 1/2 at squared. Now, if I look at my variable list, my initial velocity here is 0. So 0 multiplied by time, which time is 12.6, 0 multiplied by any value is all going to multiply out to 0. So I can simplify my equation down to this. Delta x is equal to 1/2 at squared. Because my initial velocity is 0. I can't always do that, but I can here because of that initial velocity. So now it's a matter of just plugging in what we know because our equation was already written in terms of delta x. So delta x, which is a vector, 1/2 multiplied by our acceleration, 3.08 meters per second squared, multiplied by our time value squared, so 12.6 seconds, quantity squared. So now I'll just plug in for delta x and see what we get. So we've got 1/2 multiplied by 3.08 multiplied by 12.6 squared. I get approximately 244.49. I'm going to go ahead and call that 244.5. I know usually we go to 3 sig figs. I'm going to go to 4 just to be a little bit more precise here. So that tells me that during this interval, part A, we're traveling a total of 244.5 meters. And it is worth noting that the displacement is a vector, so our value can be positive or negative. So this tells us we're traveling in the x direction out to the right. Okay, so that should cover part A. I'm going to come down here. I'm going to try to keep these all on the same page. Now we're going to go to part B, the second part of our journey. And I'll kind of do a similar layout here. Displacement, which is what I want. Initial velocity, final velocity, acceleration, and time. Okay, we're told now we're traveling at a constant velocity of 38.808 meters per second for the next 0.824 minutes. Okay, so that tells me my velocity is 38.808. And we're told that's a constant, which means we're going to start and stop at that same velocity. Okay, and then we're told a time of 0.824 minutes. So 0.824 minutes, and then I do know that there are 60 seconds. Let me space this up a little bit per 1 minute. I'm just going to go ahead and make that conversion real quick. So it should be about 30 or 40 seconds. 0.824, 60, about 49.44 seconds. Just so I make sure I have an appropriate time limit here. We're also told we're going at a constant velocity, which means our acceleration is 0 meters per second squared. Okay, so what equation should we use here? This is a little bit different because this is a situation where we have all of our variables. So that really means we can use any equation that we want to. So, what equation would best fit our scenario? Well, if I look at my list of kinematic equations, I won't use equation 1 because equation 1 doesn't have a delta x term. So I can't use that to find delta x because it doesn't have the p speed. I could use equation 2 or 3 or 4. I might like those a little bit better than 5 because 5 delta x is kind of wrapped up in another part of our equation. It's not by itself. 2, 3, and 4 might work relatively simply. Realistically, it's not going to matter which equation you use, and I'll kind of show you why. So if I go with equation number 2, that would be delta x is equal to initial velocity times time plus 1/2 a t squared. What that's going to work out to be is this. My acceleration term is 0, so 1/2 multiplied by 0 multiplied by t squared. All of that goes to 0, and then I end up getting an equation that looks like the displacement is initial velocity multiplied by time. That's kind of what my equation works itself down to if I choose equation 2. If I choose equation 3, I've got something like delta x is equal to final velocity times time minus 1/2 a t squared. And again, similar idea. Well, my acceleration term is 0, so 1/2 times 0 times t squared, that all multiplies to 0, and I get delta x is equal to final velocity times time, which again, my initial and final velocities are the same here, and my time is the same. So I could use either equation and things would work out just fine. Now the last one, equation number 4, if I chose equation 4, I've got delta x is equal to 1/2 v1 plus v0 times t. How does that work out to be the same? Well, look back at your equation. Technically my v0 and v1 are the same value. So what I could do here is I could write delta x is equal to 1/2, and then rather than calling them v1 and v0, they're the same values. What if I just call them each v? I have like v plus v times t. Well, v plus v is going to be 2v, so I'd have 1/2 multiplied by 2v multiplied by t. 1/2 times 2 is going to be 1, and I get delta x is equal to my velocity multiplied by my time. And I really don't have to, in this situation, distinguish as much, which is my initial, which is my final velocity, because those terms are the same. So no matter what I do, I'm going to end up getting an equation that is displacement is equal to velocity times time. Now, I cannot emphasize this enough. I mean, this is only applicable if our acceleration is 0. Okay? Oftentimes, in fact, very oftentimes, our acceleration will not be 0. I don't want us to get in the habit of using displacement is velocity times time, or even more commonly, velocity is displacement over time, or distance over time is how a lot of people view it. That's only if your object is moving at 0 acceleration, at a constant velocity. And we can't use that very often. Looks like I might have bumped into the board and erased something. Okay? But again, this is good if our acceleration term is 0. Now we see why. So I'm still plugging in the values that I have. My displacement, delta x, is equal to my velocity, which doesn't really matter which one I choose here because they're both the same. So I'll go 38.808 meters per second. Multiplied by time. I'm going to go ahead and erase some of this so I can have a little bit more space here. There we go. Multiplied by my time, which is 0, not 0, sorry, I was looking at my time in minutes. 49.44 seconds. So now my delta x, my displacement term, 38.808, let's see what I get. Multiplied by 49.44, I get 1,918.6. I'm going to go 18.6, actually 6.6, so I'll go 0.7. Again, usually we go to 3 sig figs. I'm going to wait and do that rounding until the very end. So here's my delta x for part B. So I've got part A, which tells me I'm at about 244. Okay? I've got part B, which tells me at about 1918. If I add those together, I'm going to get somewhere in the ballpark of about 2100-ish, close to 2200. So we've got our first two parts. Let's look now at our last one. So we've got now a little more space. Part C. This one's a little bit trickier because it tells us we have a negative acceleration. So we're told we have a constant negative acceleration of negative 11.8 meters per second squared for 4.09 seconds. So our delta x is what we're going to look for here. Oh, don't know a value there, so we'll just leave it blank, put a star. V0, V1, acceleration, and time. Okay, so let's see what we've got here. Okay. Okay, so we've got our acceleration is negative 11.8 meters per second squared. And then we've got, looks like our time, 4.09 seconds. We're looking for delta x. You might be asking yourself, am I missing something here? Like, is there a variable I don't have? Well, remember what we're told in part B, that we're moving at a constant velocity of 38.808. We can assume that that is our starting velocity here. 38.808 meters per second. And then we're going to, well, slow down. We have a constant negative acceleration, which means if I'm moving to the right, my acceleration is negative, my object is going to slow down. And now I don't really know what my final velocity is going to be here, and I don't really care about it, so I'm going to cross that out. And that's going to tell us no v1, so we should use equation number 2, which we've used quite a bit at this point. So here we go, delta x is initial velocity multiplied by time, plus 1/2 at squared. And so hopefully this gives us a pretty good idea as to where to go. And now it's a matter of plugging in the variables that we have and solving for delta x. So I should be able to do that. I can't really cancel anything out to 0, so I'll just have to do all the math here. So delta x is initial velocity times time, so 38.808 meters per second, multiplied by, looks like 4.09 seconds, plus 1/2, our acceleration is negative 11.8 meters per second squared, multiplied by, again, 4.09 seconds, and our time value is squared. Okay, so now I should be able to solve each portion of my equation and then add those values together to get my overall delta x. Okay, so my first part is going to be 38.808 multiplied by 4.09. I get 158.72 plus 1/2 multiplied by negative 11.8 multiplied by 4.09 squared. And I get negative 98.69 meters. Okay, so now I can add those values together. Excuse me. And I get a delta x of 158.72 minus 98.69. I get 60.03. I didn't travel as far here because, again, my object was coming to a stop, or was slowing down at least, right? I was moving to the right, negative acceleration, which means our velocity is becoming more negative. It's getting closer to 0 if we're going to the right. So now I have all 3 of my delta x's, part A, part B, part C. So to find my total delta x, I'm just going to add those values together. So I'll call this delta x sub t for total is equal to delta x for part A, plus delta x for part B, plus delta x for part C. All I need to do now is just add my values together. So part A, I was at about 244.5 meters, plus part B, I was 1918.67. And then part C, I was 60.03 meters. And now I should be able to add all of my terms together. 244.5, 1918.67, and 60.03. I end up getting a value of about 2223, and it's right on point. So my total delta x, my total displacement here, should be about 2,223.2 meters. Now again, obviously your numbers are going to be different, but hopefully this gives us a pretty good idea. All we're really doing here is solving for delta x a few different ways, and these different parts of our overall kind of journey here, and then adding those delta x's together for each part to get our total. So as always, I hope this gives you a pretty good start on what to do here on this specific problem. Hey, if you have questions, feel free to reach out and let me know, but hopefully this does give you some good direction. And other than that, good luck.